Hi everyone, can everyone hear and see my slides okay?
Yep.
Great. Thanks everyone. Today I'm going to talk mostly about how to apply machine learning for dialogue systems. So before we start, we start with some of the basics about dialogue systems. Dialogue systems are really a complex system. It usually requires multiple skills. First of all, you need to understand what people say. And then once you understand, you want to look at the conversational history to plan what the robot should do. So in order to optimize your task success. So dialogue management is the process of planning. So we are talking about reinforcement learning, imitation learning that could be applied in this section. And then once you know what you're going to do, then you need to articulate into language so that people can understand you. So here we're talking about language generation. So there are various natural language neural-based models currently running. For example, conditional generation, generative adversarial models on this particular forefront. Then once we understand and being able to generate language, we're saying that conversational systems shouldn't only be typing-based system. It could be multimodal. Here we're talking that not only audio speaking available, but also vision available. Even touch or other futuristic sensors could be combined so that the system can be more aware of its situation and its user. So we can actually, based on what the user expressed, for example, frustration or distraction, and then take that into account in dialogue management. Finally, we say conversational systems have to have this common sense. When we talk to people, there is a very important skill called read between lines, which in another sense is common sense, right? As human, we have so many years of education, knowing that, for example, somebody passed away, you should say my condolences, but all these informations are not in the surface level of a conversation. So you wanted to make sure, how do we embed these structural information or unstructured information for the dialogue system to learn and perform? Finally, conversational systems are very different from human, but unfortunately, during the training, we are using human-human conversation data so that the robot is actually learning from a very different distribution when during the training while compared with the testing side. Because when during the testing, the human knows exactly they're talking to a robot. They should and expect different behavior from a human partners. So you have this really huge discrepancy between your training and testing data. So how do we bridge this gap? How do we take human factor into this? And also, as we know, there are a diverse set of users who you're going to interact with. We're talking about underserving communities, we're talking people with accents, we're talking about aging populations. They all have their different preferences and their particular need and challenges for conversational systems. How can we build systems that are adaptable to individual users? Individual user groups are very important HCI factors to consider. So another thing I wanted to talk about is conversational systems are having a wide usage. So it's not only like, oh, a system can only do customer service. Sorry. So for example, we have been building social conversational chatbots that can talk to people about any topic at any time. So here we're talking about how to build social bots that can provide entertainment usage and also providing these social buffer for task completion on various things. So here is a demo of our Alexa prize-winning chatbot that is talking to one of my students.
Our dog is named Bonsai, so he came with that name. We think it fits him pretty well.
That is a great name for a dog.
Yeah, he's kind of short, like a bonsai tree, so it works.
Tell me, how long have you had Bonsai?
We've had him for a little over a year now. Yeah.
Oh, you must be great friends.
Yeah, we are.
So here is one of the conversational systems that we had We're really seeing that my students are talking about the favorite topic about her dog. We're being able to remember the dog's name, expressing from emotional, oh, you're so cute, and so on. So this is just an entertainment. So here we come to another application that is on education. So the conversational chatbot is serving as an interviewer to train novice mechanical turkers on job interview skills. So here particularly, we're making the conversational system to encourage user when we detect that the user is lack of confidence and engagement of the task. Let's see if I can.
What would you do if you had a disagreement with a coworker? Would you prefer to settle the matter directly with your coworker, or would you report the incident to your manager?
I'd talk to the coworker so he knows what he's doing and he doesn't get in real trouble. Well, maybe if he does something really, really bad, then maybe yes, I'll report him to the manager.
And what do you think the manager would do next?
Cut his pay a little bit.
So here we have a very gay short answer.
Really know, actually.
Disengagement.
Yes, I think a lot of managers would do that.
So another application I want to show you is this one about direction giving. So this is a robot that sits in front of the elevator, gives directions.
Do you need help finding something?
Yes.
Could you tell me the room number or person you're looking for?
I think it's 4800.
To get to 4800.
No, I think it's 4300. Yeah.
Excuse me.
4300.
Go along that hallway.
I'm looking for 4300.
4300 is just down that hallway and will be the first room on your left.
Okay.
By the way, would you mind swiping your badge on the reader below so I know who I've been talking with? Can I help you find something else?
No, I think that's it. Thank you. Bye-bye.
Okay.
Bye.
Bye-bye.
So this is the same interaction on the robot's view, so we can see how the robot is perceiving the whole situation.
To get to 4800.
So here we've detected the user's lack of attention through vision and acoustics. And then we're gonna say, excuse me, to attract attention.
Excuse me.
And then once we say, excuse me, we didn't get the attention, we gotta do restarts. It's like one rephrase, 2 words, and then restart the 2 words.
Go along that hallway.
And at the end of the phrase, we get back the user attention. We can launch the instruction.
4300 is just down that hallway and will be the first room on your left.
Okay, so as we talked about, conversational systems have various domains you can apply to. We just showed you from social bot to educational bot to instructional giving. And there are also various other tasks we have been doing, such as persuading type 2 diabetes patients to do more physical activities, trying to simulate patients for suicidal visits. So these tasks are vastly different from each other. And imagine on your Amazon Alexa, you have all these small skills. All of the one skills could get considered of one particular domain or task. So this really comes into conversational system because of the diverse sets of tasks that it's handling. We're really calling for a good methods to perform domain adaptations. So this is how meta learning really comes in that could be helping conversational system community in great deal. So as we say, domain adaptation, as we define it, is that we have multiple domains, D1, D2, Dn, And then you wanted to adapt the data that collected in these domain to a new domain called DNE. So usually, one way to use the data from domain 1 to n is to give a good initialization to the domain new. You can do various things such as normal supervised learning to fine-tune, and then fine-tune the data to the new domain. So there are various ways. We're going to talk about how do we learn a good initialization for a new domain using the old one. The first paper that we had is this first paper that we applied meta-learning on dialogue generation. It's a 2019 paper. So when you look at it, the number here, it's a little bit Asian, but the idea is sort of the first one to start meta-learning in dialogue. So as we know, the traditional transfer learning is you pre-train a model on the source domains, and then you fine-tune it on target domain. The source domain, basically, you get a model that is on the average, the best among all the tasks. Well, the fine-tune on the target domain was not guaranteeing that it's the best one because the data distribution could be very different. So how do we make sure that we can maximize the efficiency of the fine-tuning? So this is basically everything we wanted to do. So we're going to apply Chelsea's previous paper, MAML, model agnostic meta-learning on this particular challenge. So when we talk about a conversational system, the traditional idea is we use a supervised learning method to build a conversational system. The input of the system is usually the dialogue context, the history of the conversation, and the output is the system's response at this particular time turn. Here, D is the training data, and M is the dialogue model. Then we would compute the loss of the conversational model. Here, we indicated at the green box. Then we update this model with basic gradient descent. While in the meta-learning setting, we first have an initialized model M. For each domain, we perform forward propagation to compute the loss, same as the supervised setting before. So here, domain is really talking about the conversational task. Here, for example, in multi-WAS, we have 7 domains or 7 tasks. Here, then we have 7, as K here equals to 7. Then we update the model for each domain based on its own loss value. So if there are 3 domains, then we have 3 one-step update models. Then we again apply forward propagation to get new losses for each of those updated models. Then finally, we sum up all these new losses and use it as the final objective function. And finally, then we use the value to do the back propagation to update the original model M. So it looks complicated, but if you follow the algorithm, it's actually very easy to implement. And the code and the data is also open sourced on webpage, on my home webpage. So another benefit of this model is that it is really applicable to any dialogue system. So because here we are saying that you can use any supervised methods to train the model. So this original paper was using the sequencity model as a dialogue system trainer model. So you can replace it with any dialogue model, such as simple talk, ARDM, or anything that you wanted to use. So here particularly, we wanted to talk a little bit about the sequencity model. So here it introduces the concept of a belief span, which records all the history slots as a summation of a context. So you basically, after encoding the context, it encodes the belief span first. So here, let's take the restaurant domain as an example. The user says something like, I want a cheap restaurant. The belief span is recording the slots and its value. Here, basically cheap, which is a very important attribute for the system to remember so that it can find the correct restaurant. Anyways, the system say, what food type do you like? I like Italian. And then Italian is another important slot. The belief span will remember Italian. So here, we really wanted to make sure that it's a sequence-to-sequence model. You can use any sequence-to-sequence model. The only thing is that your input should be previous time slots belief span plus your previous time slot response and your current user utterance. And then that will generate your current belief span. And then you use another sequence-to-sequence model that use the previous belief span plus previous user response plus current user utterance condition on the belief span you just get. And empty here is the database response. So basically, you get all these belief span and you would query the database and the database will give you a response. For example, whether such restaurant exists or not. And then you would generate your current user response. So this is one model that you can use for the supervised learning. Of course, you can swap it to any model that are trainable in supervised fashion. So let's look at how good these models can be. So the previous model in zero shot is called the SDG that uses response as C's to do the low resource training. And of course, we're also going to compare with transfer learning, which is just pre-training and then fine-tuning on mixed source data. So we can definitely see our model, which called DAML, demo for multiple learning. So here, we're really, usually when we talk about task-oriented systems, we are looking at the blue score for the generated sentence, the correctness of finding all the slots, that's entity F1, and how many apples you're gonna you will need to convert. So of course, the fewer apples, the faster you converge, so the better the model is in terms of efficiency. So our model can do fairly well if you look at compared to the SDG and transfer learning in terms of entity F1. While blue score somehow is also really tricky in terms of whenever you generate sentences. Blue score is looking at exact match of tokens, but sometimes in conversational systems, exact match tokens are not necessary. You can have totally different tokens but express similar meanings or being coherent according to context. So mostly we're looking at this entity F1. So they're doing pretty well in domain, and we do really well for unseen slots. And then we do, in terms of unseen NLG, we're doing also pretty good in terms of entity F1. When it comes to new domains, we're doing much better than the SDG and slightly better than transfer learning as well. When it comes to one-shot learning, here one-shot learning is we're talking about really we're only giving a one dialogue to the new domain. And you can really see that our models is doing much better when it comes to new domain entity F1. So we have 59 compared to 55 for this. Also, we wanted to highlight that our model is very efficient and compared to these kind of transfer learning one-shot. We only need half of the time, actually more than half of the time to converge. We also wanted to say the one-shot learning, you get 60%, which is like a one dialogue. And you get 9, you raise it up to 62. And then you keep rising until like 10%, you get almost a little bit above 81. So you really see that adding data definitely helps, but like our model starts really strong with one-shot learning. Also, we want to point it out, like at this kind of 4%, 36 dialogues, we're almost sort of going flat from there on. So then another paper we wanted to introduce you is about learning for adaptation, as we said about before. So one way is to learn a better inertialization. Then the other is to find a better sort of mapping function for the adaptation. And this paper is really about how do we find a better adaptation of projection. So as we know, and again, we have this dialogue system, we have the input and output. More generally, for any NLP task, we will have this too. Let's say here, for example, we have this conversation with different domains. We have this restaurant domain. It has the conversational sentence like, what type of food would you like? Hotel domain, what area would you like to stay in? And there is a booking the train domain, what time would you like to travel? So we can definitely see the black words are in common, right? So what would you like are very sort of in common in all these texts, while the red ones are the keywords that are differentiates from all these domains. So we, when we are actually performing a task, we should really taking care that the red one, this what we call specific tokens, and the general tokens should be assigned with different weights so that we can learn the representation more effectively during the training. Now, so basically, instead of making sure every single words, oracle is Y1, the generated sentence, generated token is Y1 prime, they should have this AI to actually weight them so that we don't make sure that when we are punishing the system that generating every token, similarly, we should have a sort of priority in terms of which token we care the most. So we wanted to decide which token the dialog system should care more about. So this particular model is what we call teacher model. So for example, we can assign different ways. The system sentence, what type of food would you like? We wanted to assign really big weights on the food slot, while the other ones are okay. Well, we assign really low score to the punctuation. For example, like and you, these are less important compared to type. So let's look at the model structure and how do we train them. So again, we have the belief span, B, T -1 is the previous utterance being -1. And CT here is the context, which is conversational history. So we also, again, we have belief span going in. The dialog system contains 2 encoders, one for previous belief span, one for dialog context. Then the model would decode the belief states for the current dialog turn, with which it can search the database. So this is one, they're going to search the database. For example, you know, the food is Italian, the location is east side of the town, then you search the database to obtain MT. Then with the search result from the database, the model would predict which dialogue act and generate corresponding system response. So the AT here is the dialogue act. And then we're gonna go through a response decoder to generate RT, which is the system response. So here we're gonna, when we generate a system response, we of course gonna take care of the previous belief span and the results of the dialogue database results, and finally the dialogue act. The teacher model really employs the same context encoder as the student model. It also contains multiple transformer encoder layers and a linear and softmax layer as decoder. So we're going to initialize the model. For each source domain, SK, a data pair is sampled from database DSK, with which the student model does forward generation and computes the cross entropy. So this is the first, for each token, you have to compute this. And then for each domain, SK, with the same data pair, the meta teacher model generates a vector of weighted WK corresponding to tokens in the ground truth system response. Then we multiply the weights with the loss we just computed, and use a reweighted loss to temporarily update the model. Here we temporarily update the model for each domain. After that, then we resample the data points for each domain and again compute the loss. But now we compute the loss with the updated student model. So this is the trick here. Then we use the weights for the teacher model to reweight the new loss and sum them up as the total loss for the whole training loop. Finally, we backpropagate the total loss to update both student model and teacher model. So here is really the teacher model is trying to pass down the weights that we learned and for the student model. Okay, then we take a look at how well we do in the evaluation. So we are still going to use MAML and then use the DAMD model from John 2019 as a baseline. And then we're using the Soloist, which was one of the state-of-the-art model from Microsoft Research. The Soloist model is very similar to Simple Todd and achieves similar results. As we see, our model, DAST, is sort of in pretty good shape in terms of blue, and also in terms of all these informed success results. So we can look at, for example, we use 80 dialogues, then we can see that we do pretty well as slightly better for MAML, but a lot better for Soloist. Again, we said it before, the blue score somehow is kind of flaky. So if our model is using some pre-training model, our generation results will be actually better. But our model is only using 80 dialogues, nothing else was used in this process in terms of data. When you increase it 400, we do a little bit better than MAML simply. So here is really talking about doing the adaptation. If we have a good projection, knowing what is important in the weighted tokens, we can do better than our previous model, MAML. Let's take a look at, do the model actually learn what is important or not? So here, for example, a sentence, do you have a preference on area? So we do find that area has 3.3 compared to other tokens only have 0.7. This one, there are value choice available in the value area. We do find that these two, value choice and value area, are considered to be important. Same thing, the restaurant is price range and their address and blah, blah. Have a good day. So here, it's not very important, so everything was quite flat. Okay, thanks everyone. We can probably take more questions here.
I have a question about the student-teacher model architecture you mentioned for the dialog domain adaptation. So in terms of like the loss function, like what do you use for the loss function? Do you take things like task success rate for the loss function?
Yeah. So of course, task success rate is the one that we optimize towards.
Okay, great. And there's a question from the audience. Chris asks, shouldn't the conversational system respond with how it really is rather than just good? For example, not many people are using me. I'm lonely.
Let me see the, can you say that again? Using what instead of the other?
Yeah, or like Chris, if you're like on the line. Yeah, I can like read it. So
let me look at the chats. Oh, good. System response was how it really is rather than just good. not many people are using them. I'm lonely. Ah, I see. This is really coming into this uncanny valley issue. First of all, as a robot, you can't really feel. So some people like us to make the bot more humanized, but some people didn't like it. So we have exactly one paper to address it, how much people are comfortable with in terms of the robot can say. First of all, there are cases when we're in the social bot competition. We made the bot say that, oh, I really like the theme song of Titanic. Whenever I heard it, I would cry. And people would say, you can't cry, you don't have eyes. So there will be some people saying, on the other side, saying, yeah, it also made me emotional. So it really is depending on who is talking to the chatbot. So that's why we're really stressing on that we want a personalization for each individual. So they all have a chatbot they are willing to talk about.
Great, thanks. And another question, based on your experience, how stable meta-learning is, or how stable is it to train a meta-learning model applied to the conversational system or the dialogue management? And yeah, and specifically based on your experience, the models sensitive to, for example, hyperparameters? Do you need extensive hyperparameter search, or do you have any like tips for training a meta-learning model?
Yeah, that's a good question. Yes, it's not easy to train these models. Sometimes it really is requiring a lot of hyperparameter search. But we're able to reproduce all the results easily. And then we have the code available on our websites. If you go to my homepage, you can see the code, you can see the weights for the final models. So I think one of the key really is on when you're training it, you want to make sure that you do the tuning smartly so you don't like do the grid search. And also at the same time, keep a really nice log so you can go back to it.
Cool. And we have another question from the audience. Kenji asks, how is the training data size for adaptation? I assume meta-learning works only for small data.
Yeah, so what we were trying to say is we wanted to sort of use very small data in order to get really good results. So here, that's why we have one dialogue as in the new domain, and then we gradually improve, add more. So yes, you can also add in more conversation. You can still make it work. It's just the benefit of the meta learning would diminish, as we had in one of the slides before, right? So we have this 1% to 10% of the data. And when it reaches 4%, it almost flat afterwards.
I saw Daniel put up his hands. Daniel, do you want to?
Yeah, first, thank you, Professor. It was a great talk and very interesting. And I also have one question. So if I'm a student like who want to start experiment with meta learning or meta learning plus dialogue management, like is there any other like libraries or benchmark you suggest that people can start working with?
Yeah, you can start working with by looking at the two papers that we have and the corresponding code and data. So in terms of conversation data, we're mostly using a database called multi-WAS that everybody is competing on that particular task domain that have 7 domains. And then we have, so you can just download the code and the data from our webpage and start working on it. So some of the easy, I would say, entry-level sort of algorithm you can start with is MAML, which is a model-free, model-agnostic algorithm.
I see. Thank you.
I think Kenji has a follow-up question. He says compared to fine-tuning.
Yeah, the same thing. It's just you have smaller data, then the meta learning would appear more superior compared to fine-tuning. Then once you have all the data, basically you're doing fine-tuning, right? Except that you have some of these kind of sort of better initialization to start with. But after a certain amount of data, you're almost converging on fine-tuning.
Great. And then Hong Yi asks, in Dialog, I think people usually also consider reinforcement learning. I found that all the Dialog systems presented here are based on supervised learning. Is there any Dialog work using meta-learning in RL?
Yeah, it's a good question. So dialogue policy planning, a lot of them are could consider in reinforcement learning. But one of the problem with reinforcement learning is that you have to have a user simulator or world simulator, depends on which area you're from. That really requires a lot of efforts, but potentially here you could use reinforcement learning. But here, nothing is really stopping us using reinforcement learning and meta learning together. It's really about if we couldn't really have a good user simulator to give it a better reward. So that's why most of the current, if you look at state-of-the-art models, are still using supervised model. But of course, we are looking at definitely better models. Mostly is that we don't have a good user simulator. So that's why it's hard to train reinforcement learning algorithm well. So previously we have been doing a lot of reinforcement learning work, but more more constrained domains, such as like 20 question games and so on, that has a good simulation environment. But for these kind of really free form conversations, it's really hard to simulate how the user would react. If you are able to do that, then you already have a good system. So this is really a chicken and egg problem.
Thanks. And then Gary asks, is it possible to deploy MAML in zero-shot dialogue setting?
Yeah, that's a really good question. So we only tried it with, you have to give it a sample, basically, to get it working. If it's a zero shot, what we can do is as similar to the previous work, you can use a task description to maybe simulate a conversation to start with. But it's sort of only a trick, but theoretically, you can do zero shot.
Great. Cyprian asks, how big are the networks you are using? Is MAML viable to do meta-learning with large neural network architectures?
Yeah, we're using very big neural network models, so it's totally fine. So it's theoretically, it doesn't really constrain on how big of your architecture is. So we're using transformer-based model mostly. So here we're not using pre-training models, but you obviously can combine pre-training models in it.
Great, thanks. Any other questions from the audience for Professor Yu? Cool. Yeah, so thank you, Professor Yu, for the great talk. So our next session will start at 10 a.m. Eastern Standard Time. So we can take 3 minutes of break and we will come back at 10.